All right, so we are back. Let me pull up some notes real quick. Let me go to this. I don't know what happened with the lights. I don't know if I hit the button accidentally or something. Y'all want the lights all the way on, or? Okay. All right, I want to go back to this bridge. I know you all are probably getting a little tired of looking at it, but it's serving us so far as a pretty straightforward example for calculation. And I want to look at the computation of two quantities for this bridge, MP and MY. This is a pretty straightforward calculation. For MP, I think you're going to see how incredibly simple it is. For MY, we're actually going to have to go back and refer to those moments and shears that we distributed, a while back. Because we need some of those moments in order to compute MY. Remember, composite beams, we have to track that progression of load, so we'll need those moments. For now, for MP, it doesn't matter. So remember, here's our beam. We're going to look at an exterior girder because the effective flange width is smaller. If you recall, the effective flange width for an exterior girder, I think it was 102 inches. For an interior girder, it was 120. So the exterior girders are theoretically weaker. Okay. What else? I'm also going to look at just the positive bending region. The negative bending region would be very similar, only you would not consider the deck at all, and you would just consider one layer of rebar here and one layer of rebar there. Those two layers of rebar, and that's it. So let's go into this plastic moment calc, and I think you'll see it's pretty straightforward. So maybe what I ought to do is say MP composite beam. MP for a composite beam. Okay. So here's our section, okay? All right, we have this, we have this, we have this. Okay, now, if you recall, let's see, this is 16 by 1.25. This is 42 by 7/16. This is 14 by 3/4. And this slab, okay, so it's 102 inches. How thick is it? Is it 8 or is it 8.5? 8. We're looking at resistance, okay? We don't consider the 8.5. The only time we consider that 8.5 is when we're applying the load. We cannot count on that ½ inch for resistance computations. Now, the last thing that I think is worth mentioning, let's recall that distance is what? 2 inches. Okay, that's going to help us out quite a bit. Okay, now, what I want you to do right now is I want you to pull your Appendix D out. And I want you to look at that big table for the case 1, case 2, case 3, all that. It should be the last code handout you got from me. And it'll say Fundamental Calculations of Flexural Members. Should look something like this. Should look something about like that. Okay? Now, I want to look at this first table, and it says calculation of Y and MP for sections in positive flexure. Now, the first thing we got to do is we got to figure out what case governs. Okay. Now, remember, we're only going to really have case 1, case 2, and case 3, because none of that rebar stuff is going to matter for us since we're looking at positive bending, and we're going to assume all the rebar terms go to 0. Okay. Now, the first thing we need to do is compute these plastic forces: P sub T, P sub W, P sub C, P sub S. Now, how do you compute those plastic forces? Well, go on to the next page. And it's funny how they're all right there. Okay? Now, in short, P sub S is the plastic force in the slab. 0.85 FC prime times the area. The rest of those are plastic force in the compression flange, plastic force in the web, plastic force in the tensile flange. Notice how the formulas are assuming that you could have different yield stresses across the board. You could have a 70 KSI compression flange, a 50 KSI web, and a 100 KSI tension flange. It wouldn't matter. You could still use this specification. All right, sound good? All right. So here's our section. We're in positive bending. So this is the compression flange up top. This is the tensile flange on the bottom. If we were at the pier, that would be flipped, right? Because the beam would be going like that. This would be the tension flange. That would be the compression flange. Sound good? All right. So let's start off with these plastic forces. So let's do P sub S. So that's 0.85 times FC prime times BS times TS. Now, a reasonable FC prime, unless you're otherwise told for a bridge slab, is, or told otherwise, would be 4 KSI. And that's sort of the minimum standard anyways, times 102 inches times 8 inches. And what does that yield? Oh. Yep. 2774 kips, right? Sound good? All right. Now for the compressive flange, let's just keep this simple. It's just going to be, excuse me, 50 KSI, 14 inches, 3/4. And what is that? That's 3/4. That's not, I know that's a little weird. 525. All right. PW. Is going to be, oh, sorry, I should have written it out. 50 KSI, 42 inches times 7/16, which I figure you all can probably figure that out. And what is that? There we go. And then PT is that, which is going to be 1,000. Okay. So far, so good? Okay. Now what I want you to do is I want you to go to case 1. We're going to start at case 1. If that doesn't work, we're going to try case 2. If case 2 doesn't work, we're going to try case 3. All right. So far, so good? All right. So for case 1, what is our test? Okay. We have, let's see what, case 1. Or maybe I should use the Roman numerals. Case 1, what is it? PT, you tell, has to be greater than or equal to PC plus PS, plus all the rebar stuff, right, which we're neglecting, right? We're not worrying about that, okay? So let's check that out, okay? What's PT? It's 1,000 kips plus 918.75 has to be greater than or equal to 525 plus 2774. So on the left side, I've got like 1918.75 greater than or equal to what? 32.99. Is that statement true? No. So, no good. Case 1 is invalid. Case 2. Case 2 is similar. Case 2 says that it's similar in form. PT plus PW plus PC has to be greater than or equal to PS. Let's see if this is true. All right, 1,000 kips plus 918.75 plus 525 has to be greater than or equal to, all right. So what do we have here on the left side? All right. Is that statement true? No. All right. If case 1 is not true and case 2 is not true, what does that mean? We're in case 3, okay? So case 3 governs. And what that means is that tells us that the PNA is in the slab. All right? Sound good? Now, if the PNA is in the slab, the first thing that we can do is compute Y bar. Now, I don't want you to get confused thinking that's the centroid. That's not the centroid. It's the location of the PNA. Okay. Now, I propose to compute that. It's going to be the following. It's going to be the slab thickness times the following expression. PC plus PW plus PT all over PS. Now, what am I missing? I'm missing the PRB and the PRT terms, right? And I took those out because they're 0. We're not considering the reinforcement. All right? So far, so good? Starting to get a feeling how this is a very spreadsheetable calculation. Nudge, nudge, wink, wink. Make sense? All right. So, what we have? 8 inches times 525. Yeah, you're exactly right. Let me write all this out though. Let's see. Plus 918.75 plus 1,000 all over 2774. And you're right, it came out to 7.048 inches. So far, so good? Excuse me. All right. Not too bad, right? Okay. All right. Now that is Y bar, okay? Now, I propose to you that the formula for MP is as follows. I propose to you that it is Y bar squared PS over 2TS plus PC DC plus PW DW plus PT DT. So far, so good? And again, where am I getting that? All I'm doing is I'm going here to my table, and I'm saying, okay, I'm in case 3, so here's my expression right here, right next to case 3, and I'm just setting these terms equal to 0, right? That's plug and chug. I just wrote it down. Okay. Now, what don't we know? We can plug and chug right now, except for one thing. We don't know those little d distances, right? The d distances. Okay. So far, so good? Okay. All right. All right. So let's look at those d distances. All right. We might work backwards just because it might be a little easier to understand, and that's fine. Let's see. So here's my section. Let's go back to this. Okay. Now, where was the PNA? In the slab. So the PNA is somewhere right here. Okay? This is the PNA. I propose to you that its exact location is Y bar from the top. Now, how did I get that? Well, if I go to the spec and I look down at the bottom of that page, it tells me that anywhere from case 3 to case 7, Y bar is in the slab and it's measured from the top down. Make sense? So I propose to you that from the top down is Y bar. So far, so good? Any questions? All right. Now, let's take a simple instance. All right, so let me write this out real quick. This is 14 by 3/4. This is 42 by 7/16. And this is 16 by 1 1/4, right? This is 102 by 8. And then that distance, 2 inches. So far, so good? Okay. I'm going to start off with the tensile flange, which is the one on the bottom. Would you agree that the tensile flange is its centroid, its center, is somewhere about right there? I propose to you that dt is this distance right here. That is dt. The distance from the center of that flange to the PNA. Okay? Make sense? Now, here's how I'm going to compute that. Watch this. I'm going to go from the top all the way down to here. So the top all the way to there, and then I'm going to subtract Y bar. Does that make sense? So, what would the formula look like? Let's write that out. dt. I propose, what would it look like? We've got to go, well, I'm going to use the formula. I'm actually going to do the formula. I'm going to say T sub s, okay, plus what? The haunch. Plus what? The web. We don't add that flange thickness, right? The whole web plus that thickness over 2, right? Minus Y bar. Here, let me minus Y bar. Make sense? So that's going to be 8 inches plus 2 inches plus 42 inches plus 1.25. Well, 0.625, yeah. Minus 7.048, right? There we go, yeah. 45 point, what was that, like 577, something like that? Something like that, okay. Excuse me. Make sense? Not bad, right? Okay. That's dt. Somebody else give me DW. Let's do DW right here. So what's that? So we go down the slab thickness, right? Then we do what? We go a haunch plus what? The whole depth over 2 minus y bar. Make sense? Simple, right? So 8 inches plus 2 inches plus 42. Okay, all right, yeah, minus 7.048. And you got 23.95, what, 2? Something like that, 23.952. Sound good? Now, here's where you got to pay attention. D sub C. Okay, now watch what I'm going to do. I'm going to start at the top, and I'm going to say, all right, I'm going to go slab thickness. I'm going to go haunch. Then what? Minus the top flange thickness over 2 minus y bar. Does that make sense? I got to bring that back up. So this should be a pretty small number. What do you got? 2.57. There you go, like 2.5 inches. Now, do we need a D sub S? It's not in the equation, is it? We don't need it. But what if we had like case 1 or case 2? Then we would need a D sub S. So my advice to you is just make sure that you understand how to determine these distances, because if you're in a different case, those formulas we just derived, they're not going to work. If you're in case 1 or case 2, they're not going to work. All right. Sound good? All right. Okay. So I propose that MP equals, we got a little bit of plug and chug ahead of us, but we'll get there. All right. So we have, actually let me do this. So we have y squared, which is 7.048 squared times P sub S, and P sub S was 2774 kips, right? And then 2 divided by 8 inches. And that's that first term, plus we had PC DC, so P sub C is 525. D sub C we just did is 2.577. We got PW 918.75, 23.952 plus 1,000, and then 45.577. Oh, you're talking about the whole answer, right? Okay, okay. All right. So what'd you get? 77,519.46. So 0.5. Okay, all right. Those will say that's a long distance. All right, what are the units? Look inside the brackets to see. It's actually pretty simple. What are we taking? We're taking kips times inches, right? So inch kips. So if I want to convert this into foot kips, I divide by 12. So divide that by 12, and what do you get? 6. All right. I got like 6462.3. All right, plus or minus a foot kip because of rounding. I mean, if you use Excel, all the rounding stuff's going to wash out because you'll track your values. So that's not too bad, right? Now, I'm not saying that that is the capacity. Let me be clear about that, okay? I'm not saying that MP is the capacity. What I'm saying is that MP will be used to compute the capacity, okay? But we got a lot of stuff to talk about before we get there. So it is a slow, I don't want to say slow process, but I'm going to make it slow to ensure that everybody understands what's going on. All right? Everybody good here? Okay. Now this is MP. Let's look at MY. Okay. Now, in order to compute MY, we got to go back to our moments. So let's look at MY for a composite beam. Do I need to go back at all, though? Does everybody have all that? Okay. Let me see. Let me pull my moments up. All right. So luckily, we only need the dead load moments, so I'm going to refer to just this column right here. Let me zoom in a little bit. That's probably good enough. Okay. So this was our set of moments and shears for our bridge looking at dead loads and live loads, or permanent and transient, I should say. Now, obviously, we're looking at yield moments. All I care about is the moment. So remember, along the span, so starting at the very beginning, 9 foot away, 18 foot away, 27, so on and so forth. These are our moment diagrams if we're looking at just the dead loads. Now, at given points along the bridge, obviously the moments change. In positive bending, where's the worst case? Is it 0.1? Is it 0.6? Where is it? Say it again. 0.4, okay? If I look at these numbers, these are the largest bending moments. Everybody see that? If not, what you can do is this. Let me zoom out a little bit. I'm going to create a plot. That's good enough. Select data, and I'll do 10th points on the x-axis. Oh, put that on the wrong axis. Put the 10 points here, and put the, let's say the DC1 moments, and put those there. And hit OK. Okay. Let me take that title off. I'm going to format that axis to, say, 0 and 2. We'll make that 0.1. Yeah, actually look at every one of them. And if you look and you zoom in, you can actually look at it and see that the highest moments are at 0.4. See what I mean? So everybody okay with that? Again, what you're looking at is the moment diagram for this section. All right, everybody good? So I propose we take the 0.4 moments to get sort of our largest moments for the purposes of a design check later. All right? So what are those? Well, DC1 is what? Like 702.74. DC2 is like 146.08. And DW is 119.39. Everybody okay with that? So you see where I'm getting these, right? Okay. All right. So if you use a software program, you know, like a MDX or a LARS or something like that, it's just going to compute an MY everywhere, every 10th point. So, because it's a big spreadsheet. No reason why it can't do that. So I'll say from analysis, all right, so MDC1 is 702.74 foot kips. MDC2 is 146.08 foot kips, and MDW is 119.39. So far, so good. Okay, now, those are the moments. Now we're going to need some section properties, okay? So I'm going to say section properties. Okay. All right. Now, while you all are writing that, let me find homework 1. Okay. See, here's my spreadsheet for the section properties. I'm in positive bending, right? Now, jog my memory. Were we looking at an interior girder or an exterior girder? Make sure y'all were paying attention. This whole, the MP and the MY, were we looking at an interior or an exterior? Exterior, because the effective flange width was shorter, right? Okay, all right. So remember, I've got non-composite properties. I've got short-term interior and exterior, long-term interior and exterior, okay? I'm not going to look at the interior properties at all, right? So far, so good? All right. What I am interested in are these section moduli. Now, help me out, just by and large. Do we have larger section moduli for the top of the section or the bottom? The top, right? Like, for instance, you know, for the composites, like this is 10,008, this is 1247, this is 2710, this is 1159. Everybody seeing that? I propose to you that by looking at these section moduli, I mean, granted, I know this one's the one that's a little bit larger. You can always check both. But I propose to you that the bottom flange in this section is probably going to yield before the top flange. And if you don't believe me, you can always go back and calculate the yield moment for the top flange and see. You'll see how this works. Right now, I'm just going to investigate the bottom flange. You'll see how the top flange works. All right. So I want to query all the bottom flange section moduli for the exterior girder. So I propose that that is for non-composite, 887.49. For short-term exterior, that is 1247.17. And for long-term exterior, 1159.78. Everybody see where I'm getting that? Your sheet is organized your way, so you'll be able to find that, you know, on your sheet however. Make sense? Okay. So, all right. So, section properties, and I'm going to put the bottom flange, or maybe I should put tension flange. Okay? We have a non-composite section modulus of 887.49, a long-term section modulus of 1159.78, short-term 1247.17. So far, so good? So, I've queried two sort of chunks of data. I've got moments from my structural analysis, and I've got my section properties from the spreadsheet that I developed way at the beginning of the semester. All right, so far, so good? All right. So I propose to you, here's what's going on. Okay, so let me go back to the specs. I'm in that Appendix D. Okay? I propose to you that if you've got a composite section, remember this, we've got to solve our equation for the yield stress of the flange. In other words, we're trying to figure out how much additional moment is going to yield this shape. Make sense? Then once we get that, add up all the moments, we got yield moment. Sound good? All right. All right. So let's go and solve for MAD. Now, here's our expression. We have that the yield stress has got to equal MD1 over SNC plus MD2 over long term plus MAD over short term. Okay, now let's test your memory banks a little bit. DC1, which section is DC1 applied to? Steel only, the non-composite section, okay? So I propose that MD1, that's going to consist of that DC1 moment. What loads are applied to the long-term composite section? DC2 and DW, right? The additional moment goes on that short-term section. But one final thing we've got to throw in there, and that's our load factors. When we compute yield moments, we're typically looking at a strength limit state. So if you recall, for DC, the load factor was what, 1.25? And then for DW, the load factor was what, 1.5? Remember that? The strength 1 load combo? So I propose this is what we've got to do. This is going to equal 1.25 MDC1 over SNC plus 1.25 MDC2 plus 1.5 MDW plus whatever additional moment is required on the short term. Now, if you want, you could throw a load factor in there, but it really wouldn't make a lot of sense because you're going to have to re-include it later when you do your yield moment. So there's no point in putting something there. I mean, if you want to put a 1.75 because it makes you feel better, go ahead. You're just going to have to include it later. So if you want to put 1.75 or 179.5, it really doesn't matter. All right, so far so good? Okay, let's plug and chug a little bit. Okay, what is 50 KSI, or what, now I'm telling you, what is the yield stress? It's 50 KSI, right? So 50 KSI, now that's kips and inches, right? Sound good? So let's look at our moments. Okay, so what do we have? 50 KSI equals 1.25 here. I'm going to move this, sorry. I'm going to need some room. 50 KSI equals, what do I have? 1.25 times MDC1. What is that? What was that? 702.74 foot kips. Y'all see where I'm getting that? Okay. Now, what am I dividing that by? A non-composite section modulus of what? What was that? 887.49. I mean, keep in mind, I'm looking at this fraction right there. So that's this. Okay? Everybody okay with that? What's wrong with that fraction, though, before I do anything? Units. I got to multiply this by 12. Does that make sense? Okay, let me erase this because I'm clean that up. All right. Let's do the next one. All right. 1.25 times MDC2. MDC2 was 146.08. See, this right here, this is one of the big reasons why we had to split up the DC1 and DC2, because they're on different sections. Plus 1.5 times 119.39. And what I can do is I can just say, let's multiply that whole freaking thing by 12 inches per foot. And all that needs to be divided by, what was that, 1159? and that is, and then we also have to add whatever our additional moment is, which is what we're solving for, over 1247. All right. Everybody understand? Now, what don't we know? Well, just that, right? Sound good? So I'm going to deal with each of these fractions one at a time. So, so this first fraction, what do you get?
11.877.
There we go. So 11 plus whatever's going on there, what do we get? 3.742 KSI plus something over 1247.17. That's a little easier to handle, isn't it? Now, can I just sort of say over here on the side what MAD equals? I propose that it equals the following: 42,878.1 inch kips. And if you don't believe me, you can plug that in, or just take 50 KSI minus that, get an answer, and then multiply it by that. Yeah. Something like close enough for government work, right? So that's in inch kips. What I'll do is go ahead and convert that to foot kips, and I propose that that is 3573.17 foot kips. Now, that's not the yield moment. That is the additional moment that was required to cause yielding. Keep in mind, there was still this MD1, MD2 on there already. That's just that extra oomph, that extra little bit of moment we needed to push it over the brink. Make sense? So the yield moment, and I'm going to introduce just a final piece of notation. I propose to you that the yield moment, which is really the yield moment for the tension flange. See where I've got M sub YT? That's the yield moment for the bottom flange. That is MD1 plus MD2 plus MAD, which is 1.25 MDC1 plus 0.25 MDC2 plus 1.5 MDW plus whatever that additional moment is. So that's why we left a load factor off there, because if you wanted, you could have included it before, but you'd have to divide it, and then now here you're multiplying it. There's no reason to put it there. So 1.25 times, put my hand out up there. .25 times 146 plus 1.5, 119.39 plus that additional moment, which we just got. It was 3573.17. And now everything's nice because all the units are consistent, and I propose that the yield moment is, you do all that grunt work, and what do you get? Something about 4813.28? 28. There we go. Foot kips. So that's your answer. Now, if you want a rough check, if this makes sense, what was MP? It was what, like 6,000 something? 6,400. Okay, so it was larger than MY, right? So right off the bat, that should make sense, okay? Now, there are some really odd girder configurations where if you have a really high elastic neutral axis, you can get a computation where my comes out larger. But that's for only checking one flange. If you go and check the other flange, you're going to find that's not the case. All right, does that make sense? Okay, so so that's your long and short of it on MP and MY. Let me just go ahead and say MYT. I just want to indicate that notation, start to throw that out to you, that that's MY for the tension flange. If you want, try it out. Try and calculate MY for the compression flange. You'll find you can get an answer. It's going to be larger. And this one's going to govern. I think you think if you apply moment, the yield moment is when you start to yield one of the flanges. And I propose to you, you will yield the tension flange before you yield the compression flange because its yield moment is smaller. Make sense? We'll take our time with this, but we will start to dig real deep into the specs, particularly 610, as the weeks progress. But next week, if all goes well, I will probably have an at-home celebration of learning for you, give you a week to do it, bring it back next week. Sound good? That's all I got. You all have a good evening. I will see you all next week.